Alrighty. Oh, hello. Is this working?
It's working.
Oh, perfect. All right. Hello, everybody. Today we will be exploring electrodischarge machining, which stands for EDM. I'm Tadio.
I'm Dana.
I'm Aiden.
So for our outline, we're going to be going through the introduction followed by the processing principle, then some applications of EDM, limitations, current research, and then conclusions.
Sorry, if you're speaking, I need you to speak into the mic, please. Thank you.
Okay, so for our presentation, we're going to be doing an introduction of EDM, followed by processing principles, some applications, limitations, current research, and then some conclusions.
Just for a quick introduction of what EDM is, it's a non-traditional manufacturing method that uses thermal energy to remove material. That replaces some of the more traditional manufacturing methods such as milling or drilling, and it requires the tool and the workpiece to typically both be conductive, and it also has a dielectric fluid in between the two. Usually EDM is associated with high operational costs, which tends to make it a little bit more expensive, but that can still be cost effective for certain situations such as really hard materials or complex geometries.
So as for the processing principle for EDM, material is going to be removed by a series of controlled electrical discharges between the tool which acts as the electrode and the workpiece, and this is going to be submerged in a dielectric fluid which is going to flush away the debris. Basically, when the voltage increases between the electrode and the workpiece, it's going to break down the dielectric fluid, releasing a spark that is going to act as an extreme localized heat zone up to 12,000 degrees Celsius. This is also a no-contact tool process, and it's also ideal for hard machining materials.
Some of the main applications of EDM, we have some of the parts of EDM that resemble traditional machining, such as EDM drilling, which I guess you can guess resembles hand drilling. There's also EDM sawing, which, as you can see in this image on the top right over here, it resembles band sawing or disc sawing, but instead of a mechanical cutting where the cutter makes contact with the material, the tool uses electrodischarge to remove material without actually contacting the workpiece through that voltage difference in the sparks. There's also EDM die milling, which just resembles traditional milling. There's a spit rotating tool that uses electrodischarge to machine material rather than an actual cutter. There's also some processes that are more unique to EDM, such as micro EDM, which we'll discuss later, EDM die sinking, which you can see on the bottom right here, which essentially makes an impression of the die by removing material from the tool, which is shaped like the die. There's also EDM of ceramics and texturing. Some of those last ones are the main applications of EDM. Just to give you a better example of what EDM is and how it works, here's that die sinking. The tool itself is machined in the shape of whatever cavity you want to remove from the workpiece, and it is slowly introduced into the workpiece and slowly gets lowered in more and more with each pass, and there's sparks that are generated between the tool and the workpiece to remove material. Similarly, we have wire EDM here, where the wire itself is the tool, and this is the workpiece right here, and sparks are generated between the wire and the workpiece through that voltage difference, which removes material. You can see it because there's this giant blue line here. That's all of the sparks being generated, which is pretty cool. You can actually see it removing material. The wire is constantly being refreshed because every time the spark is generated, that wire isn't usable anymore. So you have to add new wire every time.
So like any other machining process, EDM has several different limitations you have to keep in mind in addition to its advantages. So kind of some of the major limitations, like any other process, are cost, time, and the requirements of the industry you're machining for. I really like this figure right here because it shows kind of the niche that EDM fits into with regards to surface quality and structural dimensions of different machining applications. So like I said, one of the biggest considerations, not just for EDM, but for any machining process, is the cost, right? So the cost kind of breaks down to two major categories. You have fixed cost and variable costs. So for fixed cost, that's things like purchasing the machine, purchasing the parts, routine maintenance, things like that. And your variable cost is things like labor, different electrodes, dielectric fluids, one-off maintenance items, staff, things like that. So in addition to considering those, you also have to consider kind of what you're using EDM for, right? So if you have high production speed, if you want high production volume, if you have very specific product parameters, that's also going to increase or decrease your cost for EDM. So you have to kind of, like any other process, balance what you need with the cost that you're willing to spend on EDM. Another one, of course, is machine time limitations. So like we kind of mentioned, EDM is very good for very specific applications, but even for complex geometries, for small parts, like you can see in this picture here of wire EDM, it can take quite a while for the process to complete. Similarly, micro EDM, which is another common EDM process, it takes quite a while as well due to its low material removal rate because it requires slow movement. So because they require long process times, they're not necessarily the best suited for a lot of high volume mass production applications. And then, of course, since they take a while as well, longer machine running times increase costs because you have to do more maintenance and you have to pay your staff longer hours to work those machines. And of course, from a tool wear material limitation standpoint, the tool for the EDM machine is the electrode. So like any other machining process, it's going to wear down. So in addition to making sure that you kind of account for normal tool wear in your machining process, you have to also make sure that the electrode shape stays how you want it, or you account for the degradation to make sure that your output product is, matches the dimensions and requirements it has. EDM is also very material dependent. So you can see in this figure here, part A kind of shows molten material that resolidified after machining. Part B shows debris that got stuck on a machining surface, and part C shows cracks on a surface, all after EDM. So even though EDM is very good for certain applications, it's not perfect, so it can leave these impurities that you have to account for depending on what your product or your part that you're making is going to be used for. And of course, it has a large range of tools available, so this can complicate tool selection, but can also add expense if you need multiple tools for multiple different types of machining operations.
So current research for EDM is focused on evaluating different performance metrics for different methods and materials. So some of the methods that help with EDM are going to be ultrasonic, electrodischarge abrasive drilling, and PEDM. These are some of the ones that are currently being investigated. So ultrasonic assisted EDM is going to use an additional vibration, and this is going to help flush out debris in that spark gap, and it's also going to increase the MRR. For the abrasive drilling, that's going to use abrasives, which is going to increase the surface quality, and it's also going to help flush out additional debris in that spark gap. Powder EDM is going to add a dielectric fluid. It's going to add powder into the dielectric fluid, and this is going to increase the MRR, and it decreased the tool wear rate. As for ceramics are pretty challenging to machine just because of their brittle nature and their high hardness, and they also are poor thermal conductors. So current research is evaluating different methods to manufacture ceramics using EDM. So two popular methods are die sinking and wire EDM. So there are three material removal mechanisms. The first one is going to be melting and evaporation, which is seen in part A right here. This is going to be caused from localized high heat zones, which are going to trap the heat inside of the structure, causing recast layers, which are going to affect the mechanical properties in the workpiece. There's also thermal spalling, which is going to be caused from internal stresses, which are going to expand and contract, and this is going to cause interior crack propagation, which is going to result in large chips breaking off the workpiece, which this is going to affect the accuracy of machining ceramics. The last one is going to be C, which is melting and oxidation. This is going to be common in ceramics that oxidize. So they're going to have a porous finish in the microstructure, which is going to affect their strength, and this is caused by gaseous bubbles that form from wire EDM, and this is going to basically make them less effective for load-bearing applications.
So micro-EDM machining is a process that's utilized for the miniaturization of components. The main concern being the surface quality, which can be affected in multiple ways. One of the ways is by increasing the specific resistivity of the dielectric fluid. As you can see, increasing this property can have a drastic increase on the surface quality of the machined hole. Another way to improve this parameter is to utilize microenergy discharging. However, microenergy discharging does increase the machining time, so there is a little bit of a trade-off with that. And then adding vibrations to the process will also allow for better flushing, especially when machining micro holes, so it'll allow for less taper and increased quality. And dry EDM is a process that replaces the dielectric fluid with a gas. This gas is typically a sulfur hexafluoride and air mixture, which will allow for a high MRR, especially in comparison to either one of those gases alone. This process has a primary drawback with the particles sticking to the nozzle. This can be avoided by adding a secondary nozzle to the overall tool to avoid this. The main advantage of dry EDM is the avoidance of the environmental hazards that are posed by the dielectric fluid. The last process is ultrasonic EDM. This process utilizes ultrasonic vibrations, which can either be torsional or vibrational, to improve the overall MRR, chip evasion, and to mitigate the overall taper. Additionally, the vibrations allow for an improved tool life and less tool wear. As you can see, increasing the overall vibration level drastically improves the overall tool life. And better tool life allows for better holes to be machined because there'll be less taper within the tool, so then there'll be less taper within the micro holes. The main conclusions that we had were that EDM is advantageous for creating complex parts from hard-to-machine materials. The main industries that EDM is used for are aerospace, automotive, and biomedical, and it's used to create parts, dies, and molds. Current research is in areas such as ultrasonic EDM, EDAD, PEDM, and micro-EDM, which all aim to improve the MRR and efficiency of the process in different applications. And EDM's cost effectiveness and advantages will continue to increase as their current research and technology continue to advance.
These are our references, and then I'll open it up to any questions.
So I had a project a few years ago, and we had to get a part machined with wire EDM, and I think the minimum at the time was 6 microns for the actual wire diameter. Do you know if that's decreased at all, or are there plans for them to improve that in the future, smaller?
I'm actually not too sure. I imagine, if anything, it's gotten a little bit better, but not too much, because 6 microns is pretty small to begin with. So I think it's at least around that, if not a little bit smaller.
So what was the diameter? You show the micro hole. I don't think I see the scale on the pictures. Micro EDM? Yeah, right. Well, what was the diameter there?
I honestly don't remember the exact scale, but it was on the order of microns.
I see. Okay, I'm just curious. Question?
For my question, you talked about dry and like wet EDM. I was wondering if there's a difference between like the surface quality and like the surface finish between the two.
So dry EDM has a little bit worse like surface quality and MRR just because it's using air to flush the chips out, which is a little bit less than using a dielectric fluid. But when the parameters are altered and adjusted, they can be somewhat similar, and gas EDM has the advantage of better environmental impact.
Thank you.
I'll also add, typically the dielectric fluid helps with cooling because it is such a hot process with the sparks. And fluids typically just have a better cooling properties than gases too.
Any questions? Maybe I can ask one. I want you to ask, not me, Any? So powder. So what kind of powders and then what size? Because you don't want to short. Yeah.
I'm not sure about the sizes, but one of the powders that I was reading about was a copper powder, but it wasn't proven to be that effective just because of like the properties of the powder itself. But I know depending on what type of powder you use, it becomes more effective just from like the the properties.
Okay. Okay. Yeah, we don't want to create short, so yeah. Thank you. Any other questions? Yep.
So I was wondering what the properties of the gas are in dry EDM, and why is it able to replace the dielectric fluid?
I believe like all the gases are typically, I know some of them are like noble gases, like they use like argon also, so it's just not really gonna like ionize with the sparks, and it just allows to continue to focus the sparks to the workpiece while also somewhat flushing out the chips.
Okay, I think, that's about time. So let's thank speaker. Yeah. Yeah. Okay, next team. Yes, please.
Okay then. That might be easier actually. So, we are presenting our overview on laser welding. I am William.
I'm Ansh Patel, and
I'm Vaibhav Kumar.
Our fourth team member is sadly not here as they had to be in Texas. Anyway, here's an outline of what we're doing. Basically, what is laser welding? How does it work? What's used in laser welding? What's the state of the art and what's going to happen in the future? What's some current applications? What's some current problems? And what can we do to solve those? Then, you know, references and questions. So here, what is laser welding? Well, it's welding with a laser. You choose your wavelength and focus and power depending on the material, and you can, you know, weld things. It even works through transparent barriers like water or, you know, glass for really old stuff. Here's a nice little video. Basically it works like laser beam machining. So here's a more in-depth section how it works. The laser is focused on the surface, and the ridiculous power density melts a tiny little spot. And then some of it will vaporize too. And that fuses two pieces of metal together, and now they've been welded. You choose your beam length, well, wavelength, depending on the material, because some materials reflect things at different wavelengths.
all right, so next up is the laser welding machinery and equipment, like how it basically works. So first, let's look at the sources which have evolved over the years. The first one, like the very first the industry saw, was a CO2 laser. So they were really high power, they were really used for thicker metals and non-metallic substances. But they had longer wavelengths. So if you know anything about lasers, longer wavelength means energy per photon is really less compared to shorter wavelengths. So then came in the neodymium doped yttrium aluminum garnet laser. So that's short for ND-YAG lasers, which are shorter wavelength, suitable for metals and for more precision work. And also they were like fiber delivered. We'll talk about it in a second. That is like the most revolutionary thing laser has ever seen. And next is fiber lasers. So, okay, do not get mixed up with the fiber delivery system, because in fiber lasers, they use a fiber core to excite the doped materials in the fiber core to emit the lasers out of it. And it's the most compact, maintenance friendly, and high electrical to optical efficiency. Next would be how do you deliver the laser out of the source, right? So one of the option was mirrors and lenses. But again, you know, if you're using mirrors and lenses, you have to constantly calibrate it because they're prone to getting decalibrated, and then you would have to fix it, or you would get the really bad weld quality. So next up was optical fibers. These were the most advanced tech that has ever been used to deliver the beam. This uses, as you know, optical fiber to direct the laser straight on. So they were more flexible, they were more precise, they were more accurate. They were completely eliminated the calibration part of mirrors and lenses. Next is cooling systems. It was just air, a simple cost-effective way. Water, the only drawback of water is it has rust. And also the next step was oil and cryogenics. They are specifically used for aerospace and microelectronics, where you need really high precision and really minute details where you cannot afford to have heat-affected zones. Next was evolution of lasers. It's pretty simple. As I said, CO2 was the first one used in structural and aerospace. The neodymium ones used were pulse mode welding. Next up was fiber lasers. These are the currently most popular and most highly effective lasers currently used. And over the years, right now, the current work is going on adjustable beam shaping, where there is the tailored distribution of laser energy. So traditionally, there is just a single core where you focus the laser and it just bombards all the energy in a single spot. But instead of that, there is an outer ring associated with the core, which is around 40% of the strength of the core. The core is still at the same strength, but there's an additional layer of 40% strength of energy, which kind of conditions and preps the metal, I would say, to give it a better, smoother finishes, as you can see in the video.
The ring spurt has a better quality compared to the standard fiber laser. Next was dual beam and ring modes, which we just talked. A dual beam, of course, it's like using two beams at the same time, which are used for very, very precise applications. And next was the current research is going on around real-time control, like to constantly monitor what's going on, by using optical sensors and all. State of the art and current future. So current innovations is hybrid lasers. It's a combination of arc filler lasers and arc fillers and lasers. So arc welding and lasers are combined to give better depth to thicker materials. Next was vacuum laser, using a vacuum environment to get the laser weld done. The other one is laser beam oscillation. This is my favorite one because this uses a dynamically moving laser beam to give a smoother finish to the laser weld. So that's like this. It moves in an oscillating pattern to give a really smooth and refined finish, which is like technically we avoid the after polishing of the laser weld. And the upcoming ones are AI and machine visions. Green lasers, ultra fast lasers are like using really femtosecond ones. And next up is applications. So the applications have been really wide around ever since it came into the existence. Aerospace, electronics, and medical. The best one is medical because they can now have really precise welds without having any kind of seams, which is what a medical field requires. Next was non-metallic, where we use it for packaging and biomedical microfluids and medical devices. The best one again being the biomedical ones, where we can weld really minute polymers together without having any heat affected zones or without damaging the polymers. All right, next.
Okay, after the application, we're gonna look at the advantages and disadvantages. Advantages obviously has high precision and also minimum heat damage, which is heat affected zones. It's also fast operation, but we're gonna see that when we're operating too fast, there's a chance of humping defect, but we're gonna see about it later. There's also the fact that we are more compatible, the laser welding is more compatible with automation systems like robotics. And there's also no filler material needed, so they're clean welds. The disadvantages are like other machines, high initial equipment cost. It also requires maintenance, so we need to clean and precise joints. It's also challenging to work on thick or reflective materials as of right now. And we also need the safety. So the authorized personnel who get to work at the lasers, they need to be trained so that it's safe. Okay, now we're going to look at some challenges, some defects that we see in laser welding. First one is hot cracking and porosity. We know how hot cracking happens. It happens when rapid cooling causes cracks. And porosity is gases stuck in between the pores. There's also, when we weld dissimilar materials, we get mismatched thermal properties, which creates unnecessary stress, and also brittle intermetallic compounds. There's also humping defects, which I was talking about. When we're machining at high speeds, it destabilizes the melt pool, and we get surface irregularities because of it. These are the mitigation strategies for each of them. For hot cracking and porosity, we just tune the laser, we tune its power, speed, and beam. We could also use something like argon shielding, like we can see over here. There's also, for dissimilar materials, we could use hybrid lasers, and we could also use arc techniques. This is what a hybrid laser look like. This is a laser TIG hybrid welding system. And for humping defects, we employ dynamic beam shaping, what he was talking about. We use multi-beam systems for stable energy spread so that the spread is uniform. These are the future challenges and solutions. So to avoid incomplete fusion, we make sure that there's strict control of the laser line energy, and there's also for UFG materials, ultrafine grain materials, we need to have a more advanced thermal management. We need to cool it properly. For polymer welding limitations, so with welding the similar things, even with polymer plastics, what happens is the wavelength-tuned fiber lasers are known to improve the weld quality and also decrease the damage, which basically, the pressure-assisted techniques reduce the damage done to the plastics. And there's also new upcoming emerging innovations like AI-powered control systems, which could give you controls in real time, like he was talking about. And there's also green lasers for reflective materials like copper and aluminum. And these are our references.
Yep, here's a bunch of references. There's another page of references. We had a lot of those. And any questions?
So you touched on this a little bit actually at the end, but for handling reflective materials, you said one of the innovations was essentially switching out the laser to have a different wavelength. Does that tend to be effective? Like, do reflective materials just kind of absorb specific wavelengths, and is that just like a widespread solution? You just kind of cycle through different lasers to get something for that specific material. Does that tend to be a good solution?
So no material reflects all wavelengths of light, but sometimes they may have to treat the material surface to make it more amenable to laser welding.
Okay, thank you.
Any other questions? Yeah.
So I know with typical welding, some of it's like machine-based and automated, and some of it's handheld. Is there a handheld option for laser welding, or is it all machine?
Yes, there are handheld options. Go to the first slide again. I believe it was in the video. So you will want to be careful because you can blind someone like 100 feet away with one of these.
Yeah. Wow. Okay, I see. Very cool.
Any other questions? Maybe one more we can take. Maybe I can ask one question. I think I misheard, the vacuum. I think vacuum welding, and then you said it's more like precision or something. So how does it work? How to connect between vacuum and the precision, welding?
So for vacuums, usually whenever there is a specific metal which is very prone to getting affected by the atmospheric elements, if we use vacuum welding, we can avoid that oxidation and everything. We can use different materials like inert gases, but if you use a vacuum, we would get the same results. And also, we would prevent any kind of harmful gases to escape the controlled laser environment, because as we know, lasers technically trying to evaporate some of the material which we are welding because of its high power, which causes hazard for the operators and everyone. So it has many benefits.
Okay.
No.
Okay. All right. Thank you. If no questions, then maybe we can say thanks to speaker.
Thank you so much.
Okay, one more team.
Hello, everybody. Today we'll be presenting 3D gel printing. My name is Kevin Soto.
I'm David O'Galley.
I'm Brandon Liss.
I'm Justin Moore.
All right, so for a brief outline, we're going to go over an introduction of what 3D gel printing is, discuss the processing principle, discuss different types of 3D gel printing that have emerged, some applications, as well as limitations and future trends. So 3D gel printing is a new additive manufacturing technique that enables the printing of functional components, soft components, and bioactive components through the controlled deposition of a gel material. And those gel materials are typically polymer gels or functional particles suspended in polymer gels, with the most common type being hydrogels, which are a class of highly hydrophilic polymers, usually with the water content of around 90%. So prior to printing, the gel is formulated with any necessary additives, such as functional particles to increase biocompatibility, electrical conductivity, or any other goals. The gel is then deposited layer by layer. As it's deposited, it's cross-linked so that it's strengthened, cured, and it gets a rigid shape. And then after that, the part may be post-processed with either cleaning, sterilization, or any other necessary functional additives. Next slide. So another process that has emerged kind of alongside this is embedded printing, which involves printing inside of a gel or a viscous liquid. So you don't need supports or any other secondary sacrificial materials. The gel substrate acts as the supports, and then afterwards you just need to clean off the gel, and you can print very complex geometries without the need to waste a ton of material on supports. So a very important part of the 3D gel printing procedure is cross-linking, which is the way that the different polymer chains of the gels are linked and rigidified together. So this can be done either through physical methods or chemical methods. Physical typically involves the thermal cooling of a heated gel or other non-covalent interactions such as van der Waals forces, hydrogen bonds, or anything of that nature, whereas chemical cross-linking is covalent bonds between the different polymer chains, typically through photopolymerization, enzymatic reactions, or chemical initiators. And physical cross-linking has the advantage of being reversible, so it can be used in things like drug delivery or edible printing, where you don't necessarily want the part to be fully rigid, whereas chemical cross-linking makes a much more solid structure for use in like load-bearing parts or structural parts.
So there are four most common 3D gel printing methods. The most common of the four being extrusion-based printing. This is when a liquid or slurry is extruded through a nozzle and deposited onto a moving substrate. This is the one that is used for embedded printing operations. This method has the benefit of having a low operating cost, prototyping parts very quickly, and producing high-strength components and being very accessible to most users at the cost of producing low-resolution parts, and it is also not a very scalable operation. Stereolithography, another very common form of this, is when UV light chemically cross-links liquid resin in desired regions, and then a piston and platform assembly moves that hardened part out of the way to form the next layer. UV light could be provided by either a scanning laser system as shown in the diagram here, or with an LED display. This is more scalable than extrusion-based printing and produces high resolution parts at high strength, but requires a high operation cost and offers lower material compatibility because it requires components be compatible with photopolymerization agents. Inkjet-based printing is when gel ink is extruded through a nozzle and deposited onto a moving substrate. The extrusion pressure can be generated with a thermal element or a piezoelectric actuator. This does produce high accuracy parts at a low cost, but offers lower material compatibility because it requires low viscosity gel inks and also offers low strength components. Finally, laser assisted bioprinting is when a laser generates heat, forming a bubble that provides extrusion pressure. The expelled bio ink is then deposited onto a moving substrate. This does produce exceptional dimensional accuracy and also works with fragile biological components that may not work so well with a rigid nozzle. This does cost a lot more to operate and is very complex, making it a very inaccessible manufacturing method for most users.
So 3D printed hydrogels have made their way into a range of industries over the past 2 decades or so. 4 key applications have been seen that are significant with 3D printed hydrogels, those being biomedical engineering, soft robotics, edible printing, and consumer products. Starting off with biomedical engineering. This field has seen some of the most advanced uses of 3D printed hydrogels. This is partly because of their high water content and their extreme biocompatibility, which makes them ideal for replicating human tissue and also working within biological environments like inside of the human body. The figure here on the right shows the 4 main applications within biomedical engineering, those being tissue engineering, regenerative medicine, drug screening and toxicity testing, 3D cell culture and disease modeling, and novel devices and drug delivery systems. Now, the benefits of this is that they offer a safer and more efficient, personalized approach to healthcare. And additionally, research is even starting to look at things like printing artificial organs and custom implants, which is a huge development within this field. Next slide, please. Soft robotics is a subfield within biomedical engineering that builds robots out of flexible and compliant materials instead of rigid ones as seen with traditional robots. And this is a huge advancement because hydrogels can mimic the resilience and lifelike movement of biological tissue, making them perfect for lifelike robotic systems. These robots can be used with assistive devices, minimally invasive surgical tools, and even prosthetics, really anywhere that gentle and adaptive movement is required. Now, thanks to 3D gel printing, these designs can be built now with embedded actuators, sensors, making them a lot more comfortable with systems like this, which shows a robotic hand that can interact and actually sense soft gels, which rigid components have a really hard time with. Next slide, please. Editable printing is also called 3D food printing, and it is gaining traction thanks to its control over flavor, the nutrition profile, and as well as texture, which is otherwise hard to achieve with other vegan products. A lot of earlier attempts with hydrogels in this fell short due to poor material properties, but advancements and new mixtures have allowed us to explore things like plant-based hydrogels, as shown in this image here, which explores a pumpkin seed protein-based hydrogel mixed with an alginate, which just gives it a little bit of additional thickness and more customizability with the texture. And that has successfully mimicked animal gelatin. So it is a vegan-friendly and sustainable solution that improves thermal stability, printability, and overall sensory quality. Next slide, please. And last but not least, hydrogels are being used for large-scale production with consumer products nowadays. This image here shows a groundbreaking product called Dimengel, introduced by a company called Massivit 3D. It is a UV curable hydrogel that has allowed the fast production of full-scale parts, including furniture, toys, tools, art, conceptual designs, and other things like that. And it's already being applied in industries including automotive, marine, and architecture, where visual impact as well as customization is just as important as mechanical practicality. And this is proving that 3D gel printing isn't just a lab-scale innovation anymore, and it's becoming more industrial and a real option for end-use manufacturing.
Now, to address some limitations, the complicated rheology of hydrogels makes hydrogel printing difficult, as changing the nozzle can drastically change how that hydrogel flows and prints. And there are also scalability issues with this. Cross-linking serves as a bottleneck to manufacturing speed, as you have to wait for the cross-linking to finish or cure before printing another layer. So there are high startup costs for large-scale operations in this case. There's also non-uniformity in synthetic gels, which can decrease cell viability and biocompatibility, as well as decreasing printability. To combat these, there are some future trends that the industry is looking into, such as 4D printing, which allows hydrogels to respond to various stimuli. These are called smart materials, which greatly increase the application, specifically in nerve and tissue engineering, as the hydrogels can react to how the body moves. And then further modifying hydrogels allows you to obtain desired mechanical properties depending upon whichever application you are pursuing. And then further enhancing the nozzle design and improving droplet formation will boost scalability and increase printability. So in conclusion, hydrogels are very customizable. You can customize their rheological properties, biological properties, thermal, mechanical. And as a result of all of this customization, there's a very diverse field of applications. And then through the use of the embedded printing, there's little need for support material. So all of this combined allows 3D gel printing to be poised to revolutionize additive manufacturing once its limitations are addressed. And here are references.
Thank you. Any questions? Yeah. Sorry. 2 students there.
Why is it called 4D printing?
That's referring to like time as the 4th dimension. So it's materials that can respond to stimuli and respond in like the time domain. So it's like shape memory alloys, that kind of stuff.
So maybe her and then him.
For the soft robotics slide, which part of the actual, was it the black piece that was printed with the hydrogel, or which part of it?
I missed the start of your question. Can you repeat that? I'm sorry.
For the soft robotics slide, it was in the image. Was it that slide? The one that had like the prosthetic on it?
You're referring to this slide here, this robot here?
Sorry, I couldn't see it.
Yeah, so this is what I was referring to for this slide. So the 3D hydrogel printed portion are these black pieces that are mixed in with the rigid structures, and they have embedded actuators that are actually able to sense these soft gels. And the reason that's a big improvement with robotics is because rigid members typically have a difficult time unless you have a non-rigid sensor mounted on top on the surface, recognizing flexible and soft products like that, and they can often damage it because without that sensory capability, they have no way of knowing not to like squish those or damage them.
Do you know like a cost comparison between this and like as you said, like hard materials that are used?
I'm not sure. I know from other research papers I read, they didn't do a comparison, but I did see that soft robotics is a very expensive field at the time. The manufacturing methods are extremely expensive, so there's probably some improvement to be done there and some material optimization that could help reduce cost.
Thank you.
You're welcome.
So next up is like, as you talked about embedded printing. So as we put the prong into the substrate and we move it along, I assume that it would create some kind of void behind it. So is like, does it like? I hope it. I don't know if it like does with the kind of speed we move it, but if it does, like, will it affect the printing quality at any point or like?
It shouldn't, because since it's additive, I'll pass this on to if other people want to talk about it. But since you're printing layer by layer, and you would embed your sensor on the rigid portion and then pour on top of that, the idea is that the hydrogels would form around the actuator and you wouldn't have any voids inside of your print. Okay. But
you definitely do have to kind of move slow so that the support bath can kind of flow back in and maintain shape. And there are issues with like upflow and dimensional accuracy, where you're printing the hydrogel here and it kind of flows up a little bit, but as they're working to advance the nozzle dimensions and improve the like mechanical properties of the gels, they're working to address that.
Also, the characteristic length of the needle is very short, and the fluid, the support bath, is very viscous. So typically, all the flow surrounding that needle is very laminar, which results in a predictable flow pattern around the hydrogel that you can like fine tune to make sure that it won't affect the solidified material once it's printed.
Thank you.
So I have a question about the hydrogels too. First of all, what kind of material is hydrogel? Gel or viscous fluid? Do you have any specifics? And then also, what does the cleaning process look like once you remove it?
So hydrogels are a series of polymers. They're a very like wide family of polymers. The main characteristic is that they're highly hydrophilic side chains, so they can absorb a lot of water, up to like 90%, as I mentioned. And then what was the second question?
What does the cleaning process look like when you pull it out of the viscous fluid?
Just kind of typical disinfectant and scrubbing and sterilization procedures. You're just trying to get all of that extra residue off. It's just a inert gel, so it's not too much of a concern, but for like cleanliness, you want to remove all of it.
Thank you.
Any other question? maybe can I ask one question? So can you bring back to the previous slide, like, you know, your, no, the one you, yes. So I don't know if you can answer. So you create some S-shaped product, right, in the supporting bus. So then once you create, so this green stuff is, you know, kind of foreign material get into, right? But the bus, the range, I always feel like, you know, it doesn't go up, right? So are they chemical reacting, or what is happening here? The supporting bus top surface, you know, height does not change, right? So does it mean, are they reacting, or maybe not, but if you could explain.
So the support bath basically replaces the typical like supports that you'd see in like an FDM printing process. The support bath is typically just filled to the top of some bin, and it's not moving, and it's also typically inert. So it's just acting as like a physical way of supporting the actual printed material, so that it doesn't collapse in on itself, and it can produce like viable overhangs.
So if I precisely...
I think if you're asking if like the height of the support bath would change, I think it would, because you are displacing some of the gel with the hydrogel. This specific method isn't like chemically reacting with the support bath. You're extruding a second hydrogel inside of this either viscous liquid or secondary gel. So I guess there would be a little bit of like fluid displacement as you print the hydrogel inside of it.
I see. Thank you. If no questions, maybe we thank speaker, and then we can close today's presentation. Yep, thank you. But I have one quick announcement, okay? So Wednesday, we will have, that's going to be the last lecture, right? So we have one more team, so, you know, group 10, right? After that, I'm going to talk about the exam, you know, how the exam is going to be, you know, maybe designed or made. I have not started making, so I cannot guarantee, but I will try to, you know, share as much as I can. So if you have questions about the exam, please be prepared to bring a question, then I can answer. Okay? All right, thank you.